It is debatable what actually counts as a molecular imprinted polymer. However, a general basic consensus is a polymer that has cavities in its matrix which have been imprinted by a selected target molecule. What does this mean? Basically, the polymer is shaped and made to fit around a target, which is the template molecule. The first ideas were explored in the 1930s by Polyakov, where he used inorganic silica compounds to improve affinity when binding with benzene and toluene. Only since the 1990s has real research taken off. In science terms, this is a very new area that has not been explored greatly. However, we understand some of the potential applications that we can use MIPS for. The biggest is a biosensor, where it can measure large organic molecules qualitatively and even quantitatively. It also means that because of its rugged design, that they can be a very cheap way to analyse things such as drugs in sport, allergens and toxins, whereas usually lab analysis takes a long time and is very expensive. In regards to their composition, MIPS are a bit different from your standard polymer like styrene and such. Their ingredients contain functional monomers. These are the sites that will physically bind to the target molecule or the point of attachment. These can be covalent, so you have a formal sharing of electrons, or non-covalent, which could be ionic, hydrogen bonding, dipole-dipole bonding, and things such as this. Next, we have the template molecule, which is used to form the surrounding polymer. This is either the target molecule or a very similar one. Finally, we have the cross-linking agents. These are what join the functional monomers together to create the polymer. Without this, it would just be a target molecule attached with a few groups attached to it. The most common form of synthesis for MIPS is free radical vinyl polymerization, and this gives a broad range of monomers and cross-linkers, and it's quite easy. It generally either requires microwave induction or heat. We're just going to look very basically and quickly at a free radical polymerization in regards to MIPS. So first you need an initiator with an unpaired electron. This is a free radical and this is extremely reactive. Once you have this, then you're good because it will further react and carry on. For methacrylate based MIPS, the thermal decomposition of azo initiators is the most common source of free radicals. The next step is propagation, where the free radical initiator will react with the cross-linker to form a terminal radical which can propagate further. This will hence form a large chain, and to terminate this will have two terminal radicals reacting with each other to form one long molecule. So let's look at a biosensor. Well, a biosensor has three main things. Its sensitive element, which in this case for MIPS is the MIP itself, the transducer, which changes one form of energy to another. An example would be of a large transducer would be a speaker where you have electrical energy turning into sound energy. In real terms for our MIPS we're talking about things such as quartz crystal microbalancers and many complicated things you don't really need to know about at the moment. Finally, for the detector, what you have is something that will read the electrical signal and process it, so this could be a computer or various devices. For a real world example, we look at polyaromatic hydrocarbons and if they're found in water. This was a paper published in the early 2000s by Vienna University, and what it basically said is, when you're looking at water quality, there's obviously a few things you don't want, and sometimes as a result of industrial processes, these PAHs can get in the water supply, which is what we don't want because they can be poisonous, carcinogenic, or generally bad for the environment. So what they created is a biosensor where they created a MIP and put it on a quartz crystal microbalance. Now what this did is created a small signal when the MIP would bind to the polyaromatic hydrocarbon. This signal was then amplified, transferred to a frequency calculator, so obviously it would show how much substance had binded to the MIP, and this had gone to a computer. This is just one example of how we could use it. We could use to test water or various other substances that need to be kept at high purity. It is often said that MIPs are a lot like artificial antibodies because they're highly selective and they only bind primarily with one compound. And this has led to a development of something called pseudo-immunoassays. Now, first you need to know what an immunoassay is itself before we can move on to the MIP variant. But basically, an immunoassay is a biochemical test that uses an antibody to look for a macromolecule, usually proteins and specific proteins. This is extremely selective, but it costs a tremendous amount of money because these immunoassays generally have to be created through working with animals in the labs and collecting it from the cells and purification, and they're very fragile. They work within a small range of pHs, temperatures, because it's a biological molecule. So gives a MIPS gives a viable alternative in theory because it works in extremes of pH, high range of temperatures, goes up to 200 degrees even. It can withstand repeated cycles of use, extended storage times. That's good because compared to antibodies, it's a lot more hardy. Unfortunately, in their present state, MIPS aren't a very good alternative. That's why there's a lot of research. That's because their specificity is not as good as an antibody. Their affinity for binding isn't as great. So the challenges we face at the moment is trying to get it as specific as an antibody. And if we can, it'll be a lot better product. However, I hasten to add there is a lot of potential in this, and that's why there's so much research in it.